So this is a short talk on the invisibility of time dilation. I should have done this video a long time ago. It's another problem with special relativity, and there are lots of problems with special relativity, and time dilation is invisible. And by the way, length contraction is invisible as well, and that was dealt with in a previous video. This is the article dealing with the invisibility of time dilation. It's published in 2021. And the paper says in the abstract, recently the physics education community has taken a keen interest in modernising physics education, because in my view, and probably in others, physics education is a bit of a mess. It carries on, however, while topics in modern physics have a great potential to engage students, these topics are abstract and hard to visualise. Therefore, many students hold mistaken pictures and misconceptions which can impede learning. Now, actually, the misconceptions and so forth are really what are being taught to the physics students. So, to properly understand the subject, the people teaching the subject are not doing a very good job. Anyway, in the article it continues, we expose a pervasive misconception about relativistic time dilation by presenting a thought experiment illustrating the difference between visual observation and coordinate measurement. So when you're in special relativity and so forth, you're really talking about a difference between what you actually see and what you measure. And the article carries on. We also point out how existing language can mislead and confuse students. Well, that's again what those people teaching relativity are doing. They're making a mess. The article continues. In response, we describe an instructional approach and that introduces world maps, world pictures and event diagrams to clarify the applicability of key equations in special relativity for improved understanding. By unpacking the invisibility of time dilation from the perspectives of both physics and pedagogy, we aim to help teachers provide clearer instruction. So basically, those that are teaching are making a mess of it. So the paper continues, in the face of tremendous scientific and societal challenges, physicists and educators have called for educational shifts to infuse society with science-educated citizens who are able to make more informed decisions. Blandford and Thorne note that a transformation of physics education can only happen successfully if physicists and educators work together as a community with common goals. In this context, they have called on the community to broaden, expand and revamp physics education. And my comment on that is they've got to revamp physics education to get it away from being the mess it is in now. The paper continues, Einsteinian physics, which he thinks is quantum physics and relativity, and well, generally it's Einsteinian physics is really just relativity. Quantum physics went in a bit of a different direction to what Einstein was talking about. But anyway, has emerged as a domain in which physicists and educators have actively shared, developed and discussed instructional models and pedagogical approaches to improve educational practices. Einsteinian physics presents excellent opportunities to engage students and foster positive attitudes towards science, because students perceive Einsteinian topics to be more relevant than topics of traditional school physics. It is natural for those learning such abstract concepts to want to picture what is going on. However, many Einsteinian phenomena are invisible to the naked eye and defy students' everyday experiences. Examples include curved space-time, cosmic expansion, and warped time. So basically all these things they're talking about, curved space-time, cosmic expansion and so forth, are really invisible to a large extent. It's just theoretical constructs. Now moving on to the summary, it says, since relativistic phenomena are hard to visualize, students often hold mistaken pictures. Specifically, confusion between what we see and what we measure can lead to persistent misconceptions around length contraction and time dilation. And it's, as I'm pointing out, that there is a difference between what we see and what we measure. It goes on, as well as more general confusion about special relativity, and I'm saying this, existing physics education is creating that with its students. The history of this confusion related to length contraction indicates the issue is pervasive, as well as tricky to rectify. The lack of realization, and there is a similar issue around time dilation, suggests the problem is subtle. In this article, we expose this pervasive misconception about time dilation. We present a familiar thought experiment demonstrating the invisibility of time dilation and show how the language of special relativity can mislead students and educators, hence why the physics education is a mess. In response, we describe an approach that introduces world maps, world pictures, and event diagrams as useful instructional tools. By unpacking the invisibility of time dilation from the perspective of both the physics and the pedagogy, we aim to support teachers who wish to bring one of the most striking features of Einstein's theory of relativity into their classrooms. We hope future work will investigate this further, so forth. So the teaching of relativity has been dumbed down in general. They don't go into this issue of there's a difference between seeing and measuring, hence why the students taught it go away with misconceptions about the subject. And it is that it's not emphasized enough in the education system about this difference. The paper goes into detail about the maths, which I won't go into because I might disagree with it, and I am only pointing out here the invisibility bit of the time dilation. And also, in my view, time dilation is misnamed. It should really be called something like clock dilation. And as I pointed out in other videos, it's making a mess of the subject of relativity because it's moving goalposts all the time. You're suddenly moving your goalpost from saying, oh, it's observer seeing time dilation, to suddenly moving to say, no, it's the observer doesn't see time dilation, what the observer does is measure time dilation. And so it's this subtle difference that is moving the goalpost in this relevant part. And moving goalposts is really cheating. It's making changes all the time to what you're saying special relativity is. Thank you. I finished. This is the end of this little video.